So the next topic is when we have qualitative predictors. So for example, if we have, let's say, in our data set, let's say this is the first instance. And for this first instance, we have the square feet of a house. That would be x1. And then we have the number of bedrooms. And y is the price. So maybe, let's say there's a condo 800 square feet with 1 bedroom, and that's $1 million, right? So it's in $1 million. The second observation, this is like 1,000 square feet. It's 2 bedrooms, and it is 1.2 million, right? So in here, x1 is continuous, but x2 is discrete. Right? As x2 is discrete, we kind of need a different process for using it in a regression model. So if we want to use a regression of x1 and x2, let's say values of x2 are either 1 or 2 or 3 or 4. As x2 is a discrete variable with 4 levels, so we call this 4 levels, we need 3 dummy variables. So these are essentially the dummy variables. The dummy variables are meant to kind of code what the value of x2 is. So this is, for example, how we can code this. When x2 is 1, we use that as a baseline. Therefore, we don't need any dummy variable. The software actually takes care of this for us, but we need to know what software is doing to understand its result. So we need to take one of these levels as the baseline, and actually it doesn't matter, for fitness of our model. Then maybe for value 2, we use the dummy variable that has, let's say, beta 2. When the number of bedrooms is 3, we use beta 3. When the number of bedrooms is 4, we use beta 4. Then our model will be something like this. There will be some intercept in all situations. And if the number of bedrooms is 1, no dummy is needed. So the next thing we can write is just beta 1 times x1, which was a continuous variable. And this is the situation when x2 is 1, number of bedrooms is 1. Then if the number of bedrooms is 2, we need something like this. If x2 is 3, we need beta 0, beta 1, x1 plus beta 3. And as you may imagine, when we have x2 being equal to 4, we need a beta 4. So for all of these models, as you can see, the slope is the same, because we only had one continuous variable, and the slope is needed as a coefficient of that continuous variable. So this is continuous because it can take any value. We can also have like some number that is not round. We can have 799.56, whatever, right? This is not necessarily just an integer. But this one is an integer and one of these 4 possibilities, nothing other than this. We don't even have 1.5, right? As there are just 4 cases, we use a qualitative variable for it. And in this case, actually, the qualitative variable is ordinal, meaning that there's some order to it. 2 bedrooms is more than 1 bedroom. 3 bedrooms is more than 2 bedrooms, right? But we also have qualitative variables where there's no order, right? We have ethnicity. We have gender, right? When there is no order, right? But here, as these are still, values, there's some order to them. But we can also have, other qualitative variables that have some order, but are not just numbers. So let's say, like orders in the military, right? We have like general, we have colonel, and so on. All right, but the difference between these cases is actually in the intercept. So the intercept is simply the kind of baseline for a 1-bedroom apartment, a 2-bedroom apartment, 3-bedroom apartment, 4-bedroom apartment. So you've seen when people report housing prices in Toronto, they report these things separately. They say the average price of a 1-bedroom apartment is this. They're talking about this kind of regression function. Then separately, they report another value for 2-bedroom, because that's a different thing, as if it needs a different polynomial function, right? And then the regression functions we're going to get will have x1 and y. They all have the same slope, but the intercepts are different. Let's say this is beta 0. So beta 0 means the intercept of a one-bedroom apartment. It means where the line of one-bedroom apartment hits the vertical axis. This means that even if there was such a thing as a one-bedroom apartment with square feet 0, the price wouldn't be 0. You know, it starts even the smallest observation we have, even the smallest one-bedroom apartment in Toronto starts from, you know, some non-zero value if we kind of extrapolate that. So these are all x's. Let's say we represent the two-bedroom apartments with squares. So then the squares that we have will create a line with the same slope, because x is just square feet of a house, it's just size of a house, right? But here the intercept will be beta 0 plus beta 2. Let's say for three-bedroom apartments we use triangles, then maybe all the triangles we have in our data set, they eventually give us this line with the same slope, but the intercept is beta 0 plus beta 3. And similarly for this last one, again there will be some line. Let's say we represent these ones with circles. These are where the circles are. So you can see all of them have the same slope. So this is the case. Sorry, I have a question. So this is a case where there's no interaction between these variables, but we can actually make the model even more complicated if we include an interaction term, which can be something like an additional column where we multiply, for example, x1 to x2. This is as if there's a synergy between, you know, how an apartment with more rooms and a larger size is going to have a higher price, not just because of size and number of rooms, but because of the synergy between them. If that's the situation, we may use like an interaction term like x1, x2, and that gives us a more complicated model. But you can see when, as long as there's no interaction in the model, the qualitative variable is going to give us lines with the same slope, but only different intercept. And the different intercept is, you know, because just two-bedroom apartments are more expensive than one-bedroom apartments, just generally. But also because of differences in the sizes, we have these lines, right? So for example, if we compare, you know, well, I mean, if we compare these 2 points, here and here, we are comparing two apartments of the same square feet. One of them is one bedroom, one of them is two bedroom, right? The two bedroom is more expensive. This one probably has a larger living room or a larger kitchen, but this one is more expensive, right? But we can also like make a comparison horizontally. So this one and this one are, you know, a one bedroom apartment and a two bedroom apartment that have the same value, have the same price, but their sizes are quite different. So the one bedroom is so large that it becomes as expensive as a two bedroom, as a tiny two bedroom, right? So this is the situation where when there's no interaction there. But it can become more complicated if we consider something like this. When we consider something like this, it allows us to get models where not only the intercepts are different, but for one bedroom, two bedroom, three bedroom, and so on, we get lines not just with different intercepts, but with, let's say, different slopes. So here, these two have different intercepts, but also their slope is different. This is when there is some interaction like x1, x2 in the model. This means that, for example, f prime is beta 0 plus, let's say, beta 1, x1 plus either nothing or beta 2, right? So I can write that as, I mean, I can also write it differently. But either they have beta 2 or 0, and they have some beta 3, x1, x2, right? So if we kind of expand the model, make it more complicated by including this weird combination and add a beta 3 for it, then we can have lines that look like this. So for this part, I'm just using some weird notation, but I hope you understand what I mean. So for this component, either we have 0 or a beta 2, depending on whether it's a one bedroom or a two bedroom. For a one bedroom, as it is a baseline, we don't use anything, just like here, there's no beta 2, but for a two bedroom, we have beta 2. Then because of the existence of this interaction term, we can be more flexible. So now, let's think about the data and some categorical variable. So if I have one bedrooms, these are one bedrooms, right? If we have a scatter plot on a screen, maybe these are the points that we color differently for one bedroom, and then these are the two bedrooms. These are the two bedrooms. From what you see in here, do you think we should include this term or we should not include it? Anyone can raise your hand. Yes, easy as that. So now, when you see a scatter plot with color-coded with some qualitative variable color-coded, you can see that the ideal lines are like these. As these fit better compared to two parallel lines, this is not a good modeling for this data, and this is a good modeling for this data, which means that we need to go back to our table and include this additional column. Because the additional column allows us to have two lines with separate slopes. Because the increase in price of two-bedroom apartments, when we increase the size, is not at the same speed as the increase in price of one bedroom over different sizes. So I think this is one general kind of tip that it's helpful to just look at the data, to just plot the data as a scatter plot. Actually, I think scatter plots don't receive the attention they deserve in data science. In many situations, when you have the data, even if there are many, many records, it's a good idea to just randomly take maybe 100 or 1,000 of the records and just plot them. Plot different combinations of the outcome and some predictor. Then just based on the scatter plots, sometimes you see situations where there's some predictor xi and your outcome, and there's the patterns are like this. This is a good sign that xi should be kept in the model. Whatever you want to predict, there's some association. You can see that when this one goes up, the other one goes up as well, so you keep them. For some other variable, some xj, you see that there's generally a negative trend. It means xj should also be there because there's correlation. Regardless of whether it's negative correlation or positive correlation, correlation is good for making predictions. And there are also situations where when you plot these, so the outcome based on some column in the data frame, and you see that the data is everywhere. There's no clear pattern. When you see this, just visually, roughly it gives you the idea that maybe xk is not needed. So if you just want to, just a very quick and dirty method for deciding variables, right? Deciding features, so this is feature selection. One very rough idea is to just look at the scatter plots. All right, so now for models that have interaction term. So let's go back to quantitative variables. So there could be situations where we have TV, let's say radio, the intercept, as well as TV times radio. This is the variable that we just created. So when we look at the data, maybe we see that beta hat for TV is 0.4, for radio is 0.2, for TV times radio is also something. Intercept, again, is some value, doesn't matter that much. The standard errors are like this. And the p-values are all of them are significant. So this is the same situation as this plot in here. This is the same situation as this question that you answered. You told me that for modeling this, we need this additional feature to be added to the model here. Another kind of signal for the same situation is that we fit a model where we have these three variables, and this one, the interaction, becomes significant, while we also have the main effects, TV and radio. So what this means in terms of marketing is that maybe, just again speculations, maybe people are more likely to make a purchase when they see our ad on TV and also get exposed to the ad on the radio. Then they see it, oh, it's everywhere, this brand is everywhere. And then that kind of causes them to have a behavioral change and go and purchase our product. Again, I'm talking about causation, but under speculation, because all of these are observational data, and we cannot make claims of causality with observational data. If I want to be more precise, I can say there's also association between sales and the synergy of TV and radio, meaning that if we have a fixed budget for advertising, let's say $100,000, our sale is going to increase more if we spend it half and half on TV and radio, 50,000 TV, 50,000 radio, compared to spending all of it on TV or all of it on radio, because there is synergy and we want to capitalize on this. So then in terms of interpretation, again, the interpretations when the model has interaction terms becomes even more complicated. Now we cannot say that 1 unit of TV, one unit increase in TV spending, in TV advertisement spending, leads to 40 cents increase in sales, keeping everything other fixed, because when you change TV, definitely this thing changes, right? So the interpretation becomes more complicated. And one other thing, whenever we include the interaction term of two variables, we must include the main effects as well. This is called the hierarchy principle. So even in situations when this is significant, this is significant, this is significant, this one, let's say, is not significant, 0.1, we have to include TV, because as long as it is in the interaction, the main effect must be there as well. Otherwise, this interaction might have had this significance because of the main effect of TV. So this is just a principle that we need to follow. If you remove something from the data frame, remove it, that's fine. But if you create additional variables with a combination of features, their main effects, the main columns should be also there in a regression function. Yeah?
So I have a question. I'm just wondering, for example, if we are saying to increase spendings on advertisement in this case, because as you increase the synergy term, you're also increasing the TV and the radio term.
Yeah, yes, that's right. Yeah. Here, when the model is like this, whenever we increase this one increases, and then that I mean has like two sources of impact on the model. Also for the radio, if we increase the amount we spend on radio, it has an impact through this path and through the synergy path. If we increase this, there's no way that we can increase this without increasing, I guess, at least one of these, right? So just, the factors are not independent anymore. So this is useful for modeling, for making predictions, but for having a model where we can make interpretations, actually we don't need these interaction terms because they just make things complicated. But sometimes also like in other fields, people need these interactions because it's about maybe, someone who's on two different medicines at the same time, right? So this is one like remedy for like some intervention for some medical situation, another intervention, and both of them at the same time. And these chemicals, they could have more complicated effects on the body. Therefore, in biostatistics or in medicine, people always include many of these interactions because the main effects are usually studied some time ago when the drug was first introduced, right? And then many of the challenges are about looking at the combination of like different drugs, for example. Yeah. Yeah, the effect size is small, but that's kind of expected because just the fact that this is not zero, it means that kind of breaking the budget kind of equally between them is a better idea than putting all of it on TV. Of course, it depends also on the factors. If TV was, had such a huge effect, maybe we can maximize sales by just investing on TV. But the synergy just means that increase in the sale is also because of the kind of harmony between kind of capturing different media. Yeah, it's difficult to separate them. That's the idea. If you want to interpret what's going on, this is not that useful. But for making predictions, this is useful because there could be actual synergy in those variables in marketing term. And if you want to model it, we need a weird variable like this. But for the interpretation, this is difficult to interpret. So we just prefer to use different univariate regressions to just talk about sales and radio, or sales and TV. All right, I think I pretty much covered everything. Yeah, so in the next couple of lectures, then we're going to talk about classification problems. That's where y is a qualitative variable, right? Is a discrete variable. Then talk about nonlinear models, which are more complicated than this. So this was kind of introducing some nonlinearity, but the function is still linear in its own new features. So we can also have nonlinear models, and then tree-based models and regularized fitting and everything. So thanks a lot for your attention, and see you next week.